Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss another test which is performed on shunt DC motors, and this test is used to measure the stray losses, right? And this test is called retardation or running down test. In this test, motor is run first, right? Then supply is cut off from the armature only, keeping field coil excited. The armature slows down and its kinetic energy is used to meet the iron losses and mechanical losses. So in this test, first we will run the motor and then we will just cut off the supply of the armature. Then due to inertia, the armature will turn on rotating, but its speed will start decreasing, right? So retardation will be produced in the armature, and that kinetic energy which is actually present in the armature will be converted to the electrical energy due to the generator action. Since we have not cut off the field coil from the supply, so magnetic field will be constantly present in the winding, and only the armature speed will be decreasing, right? And since the armature is rotating, EMF will be induced across the armature terminals because magnetic field is also present over there, and the induced EMF of the armature will go on decreasing at as the speed of the armature decreases. Okay, so in that case, the kinetic energy of the armature will be equal to half j omega square, and this is the famous expression for the kinetic energy in angular motion. Here, j is the moment of inertia and omega is the angular velocity, and that kinetic energy will be actually used to cover the stray losses in the DC motor or DC machine, because we are not providing any mechanical or electrical input to the system. So all the energy which is present in the system or in the machine will be used to cover the losses. Okay. So in this case, the armature current is zero, so armature copper losses will be equal to zero. So only the losses which are present at this moment are equal to the stray losses, and stray losses include the mechanical losses which are friction and windage losses, and the core losses or iron losses will also be present in the system because the flux is present. And as the armature of the machine stops, both the mechanical losses and the iron losses will be equal to zero. The reason is that the friction and windage losses will be equal to zero because there is no movement, and the iron losses depend on the voltage. And since there is no EMF induced when the speed of the armature is zero, so there will be zero iron or core losses. So we have to calculate the stray losses during the instant when the armature of the motor is slowing down. After the armature has stopped completely, all the losses become equal to zero. So the losses in this case will be equal to the time rate of change of this kinetic energy. These are the power losses, and power is defined as the rate of change of energy or work. So W will be equal to d by dt half j omega square, and that is equal to j omega d omega over dt. During running down, speed will reduce and V will showing decreasing reading since E is proportional to N. So this is j omega d omega over dt, and we can translate this angular velocity to RPM, right, capital N. And after that, we can get a new expression. Okay. So omega is equal to 2 pi n by 60, and W will be equal to j omega is 2 pi n by 60, and this will be equal to d by dt of 2 pi n by 60, and after simplification, this expression will become 2 pi by 60 square j n dn by dt. So if we calculate this dn over dt, and if we know the value of j, we can calculate the stray losses at any speed, right? So at any speed, we can calculate the stray losses. So we have such a profile after switching off or after cutting off the armature winding from the supply, and the speed of the armature will start decreasing and it will take some time to reach to zero, and the slope of this straight line will give us dn by dt, right? So if we calculate the slope of this line, we can get the value of dn by dt. So if we are unable to measure the speed of the armature during this running down, or if we don't have the instrument for measuring the speed, we can still estimate this speed, because we know that in generators the induced EMF is directly proportional to the speed. So as this speed is decreasing, the induced EMF of the generator is also decreasing, and that induced EMF can be easily measured by this voltmeter. So we can get such a decreasing curve for the induced EMF or voltage, and since this voltage is proportional to the speed, we can measure the constant of proportionality over here, and then we can easily get the same curve uh, of speed by only having this voltmeter. So after having this running down curve of the speed, we can calculate its derivative, and then we can calculate these stray losses at any speed of the motor, right? So next task is to find the value of this moment of inertia, right? So this moment of inertia is yet another quantity which has to be determined, and we can have such a mechanism in which we can either eliminate this value, right, or we can indirectly measure the value of this moment of inertia. So finding this value is not very difficult. All we have to do is to just perform this test initially, right? Run the motor, then disconnect the armature from the supply and get this expression, right? We can get this dn by dt from this curve, and we can get this expression in the first step. In the second step, we have to build such a system. Okay. So in this system, this field coil will be constantly connected with the DC supply, and this is the armature winding. And this armature winding will also be connected with this DC supply. And we have to use a double throw switch over here. So this is a double throw switch. And when we turn off or when we open the switch from here, it will also be opened from this side as well, because this is a double throw switch. So in this test, we have to disconnect the armature from the supply by using these two switches or this single double throw switch, and we have to build such a system over here as well, right? So what this resistance will do after turning off these two switches, all the currents which are present in this armature, or all the energy which is present in this armature winding, will be released through this path. And in this path we have a resistor, so we can dissipate the electrical energy produced by this generator during running down across this resistance. So this will cause the kinetic energy stored in this armature to be released quickly, because we are dissipating the electrical energy through this resistor. So as a result, when the electrical energy is dissipated quickly, the kinetic energy of this armature will also be released quickly, and this armature will tend to stop in a shorter span of time as compared to the previous case in which though no such external resistance was present. So that is the most important thing which we have to consider by performing this test. Okay. So in this case, we will get second expression for W, right? And by using these two expressions, we can eliminate this J. Okay, so let's see how this happens. So S is a double throw switch. First, dN over dt1 is calculated by switching off the supply as we did in the first case. And after that, the retarding torque is produced by opening switch S, right? In the second case, we have to use this circuit, and we will open this switch so that IA flows through R. So IA will flow through this resistance and power is dissipated and motor tends to stop quickly. So in that case, W dash will be equal to IA square R plus RA, right? And W plus W dash will be equal to 2 pi by 60 square Jn dn by dt2. So dn by dt1 was the time rate of decrease of the speed in this case when no external resistance was present. In the second case, our rate of decrease of the speed will be equal to dn by dt2, right? So W plus W dash will be given by this expression. Okay, so we have obtained this second expression. W was the case when no external resistance R was present, only the armature resistance was present. And in this case, by placing this external resistance R, the armature resistance and the external resistance RA and R both are present. So in that case, we will get W plus W dash. W was the stray loss in the machine when no external resistance R was present. W dash um, is the stray loss expression when external resistance R was present. So by adding these two expressions, W and W dash, we can get this formula, and W was equal to this expression, W plus W dash is equal to this expression, and we can take the ratio of these two expressions, W plus W dash divided by W is equal to dn by dt2 divided by dn by dt1. So these terms are cancelled out and we can do the rearrangements. So this term can be taken over here, this W can be taken over here, and after simplification, we will get this expression for W, and W is equal to W dash dn by dt1 divided by dn by dt2 minus dn by dt1. So this is another way to calculate this stray loss, right? So this stray loss W can be calculated from this expression. We have all these time rate of change curves or rate of change values of this angular speed without and with the inclusion of the external resistance R. So once we have calculated this W, we can calculate the value of this J, right? So after calculating this W, this J can also be calculated. So this is the total or complete description of this retardation or running down test, which is performed on shunt machines. And this test is useful for evaluating the stray losses. So I hope you have understood the concept which is discussed in this lecture. And for watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.